Thank you. Okay, so well, first of all, thanks a lot for coming to my talk. I am going to be talking about Offload, that's what I'm going to say. The work I have been doing for the last, well, mostly the last 3 years, but most of my PhD. So, let's get started. And this work is about making mobile applications do more, reach their full potential. And I'm saying that they aren't really reaching that potential because, well, they are constrained. These mobile devices are constrained. If you look, for example, at speech translation applications, you will see that, well, what you can get is, that means if you are doing it offline, of course, it will be slow, limited, or inaccurate. If you try to do augmented reality in the way that UI designers are picturing it, with you turning your viewfinder and looking at someone and being recognized, looking at some landmark, recognizing it, it's not possible now. What you can get is, well, just your viewfinder with some GPS positions. And that's well limited compared to what they want to get. And if you look at mobile games, it turns out that they are, well, a far cry from what you can get in an Xbox 360 or in your gaming PC. And most importantly, all of these kinds of applications are very power intensive. Now, this is important because battery is a very important resource in mobile phones. This graph shows how the energy density of batteries has improved in a period of 15 years. It's more or less 2 times. And in the same time, well, CPU, for example, has improved by a factor of 250. And well, not only that, so larger screens, more sensors, stuff that really eats the battery has increased at a much faster rate. So I can say that with just battery technology, a solution to this problem is quite unlikely. And so one solution for this problem will be remote execution. And well, right now there are many solutions commercially that use think-like model. For example, you are probably familiar with Siri, that when you just speak to it and connect to the server and give you some answers. That only works when you are connected. If you are disconnected, you cannot get any. The same happens with OnLive, that is an online service that lets you play games through a more powerful server in the cloud. And the other thing you can do now is, well, do everything offline. But if you do that, well, you will get like this waiting logo all the time. So that's not something you would want. And also, you will run out of battery very fast. So now the question is there something in the middle, something we can do about it? And I say yes. But there are some challenges about doing this. First, it's not very simple to know what should be offloaded. What are these power-intensive portions of your application? And also, while the mobile environment is by definition very dynamic. So sometimes you have fast connectivity, sometimes you don't. Sometimes you have more battery. And well, even depending on where you are, you may use applications different. So any kind of dynamic approach has to adapt to these changing variables. Now, for this to take off, we need to make this very easy for developers to use. Otherwise, it wouldn't take off. Now, there is important work in this area. And the most important work I would like to mention is Cyber Fragging by Rajesh Balan from CMU in 2006. And he proposed a very interesting solution that was using a coarse-grained approach, a language-agnostic technique to work in many different languages. And it was mostly designed for interactive applications. That means you push a button, the application goes, and you get a response back. And he asked developers to specify a set of tactics in it's a pseudo language where they say more or less hint the runtime how to do this offload. And this was very nice, but for example, a coarse-grained offload leaves opportunities for fine-grained power saving. And language agnostic is not taking advantage of many language-specific features that makes this easier for developers. And as I will show, there are more than interactive applications that are important for mobile phones. And well, asking developers to do tactics is still placing kind of a high standard on amateur developers. And most important is, well, many things have changed since this work was published. And let me go about it. So what's different? First, we have a new generation of smartphones that started with the iPhone. And with these smartphones came a lot of mobile stores And with these stores came plenty of applications and applications developers that are not necessarily very experienced. For this reason, it's important to have a very simple solution. Now, we have an increasing use of managed environments, these languages like Java and C# in smartphones. So now we can probably take a more risk approach and take a fine-grained offload by using these managed languages. And while mobile gaming has been increasing dramatically in the last few years, now everyone is playing games all the time in their phones. So this kind of continuous applications is important to also support. And finally, while mobile constraints, yeah, exactly. So bandwidth has changed. Now we have like high bandwidth, like with LTE, but now the constraint is not the bandwidth per se, but how much usage you can get a month from this bandwidth. So in general, I can say that we need a new solution. And this solution should fulfill the following goals. First, it has to place a very low barrier of entry for amateur developers. It has to bring the offload benefits to not only interactive applications, but for most of the applications I just mentioned. And for this, I propose to take advantage of certain application properties. That means we are not going to do all applications, we are going to do some application-specific approaches for some specific kind of classes of applications. And we want this to adapt to these modern constraints of different bandwidths, of usage limited, etc. Now, in my solution, in the thesis statement I have is, I consider that it is possible for mobile developers to obtain very significant benefits from doing code offload by identifying just a small number of properties about their applications. And well, the first set of properties is, well, to identify what class of application you are targeting. First, we have the computation-intensive applications that will be, well, CPU-intensive, memory-intensive, in general, resource-intensive. They are interactive applications with this operation model that I mentioned. And in general, they will have complex computations if you compare them with the amount of input and output they produce. This will come down to, if it's cheaper to send this input and output over the wire than doing this operation locally, then this is a very suitable application for this approach. And on the other hand, we have graphics-intensive applications. These are GPU-intensive. They are continuous. And their output presents this nice feature of temporal locality. That means that the output changes gradually with time. For example, if you think about a game or a visualization application, you will see the output moving slowly, and the slow motion is actually a gradual change in the output. Now, for the rest of the talk, I will present two systems. Each of them will target one of these classes of applications. For the first half, I will present Maui, that is designed for handling computationally intensive applications. And for the second half, I will present Kawaii, that is a system to deal with GPU-intensive applications. So, let's get started with Maui. Well, Maui, it's all about the apps. Most general-purpose applications are the ones that are going to be handled by Maui. Here we have a graph showing the amount of applications in the App Store and downloads. As you can see, mobile applications have been increasing steadily over the last, well, 4 years, and we have now hundreds of thousands of applications and billions of downloads. So it's all about applications. We need to have a simple solution for all these developers doing all these applications to take advantage of offload in a very simple way. And it's all about the battery as well. Because as I said, power is getting exhausted very quickly, so we need to have this as a priority. In order to solve these problems, I present MAUI, which stands for Mobile Assistance Using Infrastructure. MAUI contributions with in relation to previous work is at first, it combines an extensive profile of the network, the device, and the application with an integer linear problem solver. This solver will make dynamic decisions of whether you want to run something in the cloud, well, in the server, or in the model. And it's designed first to optimize for energy reduction. Also, MAUI is taking advantage of these modern languages like Java and C# to simplify program partitioning. Unlike previous approaches like the one I was mentioning about cyber threatening, this makes us to have have the same application that we can just get the same binary thanks to the language features of .NET Transition. Now, how we get these two to communicate? Well, we have the MAUI runtime in both sides. This runtime is composed by a proxy that will accept application calls. A solver that will actually decide whether the proxy is going to send the flow of the application to the mobile or to the server. And a profiler that will gather the necessary information for this solver to decide what to do. Now, how does this look from a programmer perspective? As I said before, it is very important for the programmer to take advantage of this approach as easy as possible. So we just ask him to, well, let's build the application as a standalone application. And well, here again, coming to my statement, the developer has to identify simple properties and methods. Those that fulfill those properties will be annotated with a remote attribute. It's actually very simple. It just looks like this. You have your method, and you just have to put like this word on top. It's very simple. Now, what makes
that again, real quick?
Sure. This is a method from a chess game that will get the valid moves that you can make from any given position.
So just remote is the...
Yeah, exactly. So what makes a given method remote synchronization and lock?
So you want a quick one. You could potentially offload the sensor readings as well and let the cloud do.
Yes, you can offload the readings, the data itself, but you cannot ask the server to read the sensors over there.
Sure.
Yeah, that's what I meant. Yes. Actually, yeah, it's a good idea to offload the readings for
so
the server.
So will the profiler actually take that into account and say, okay, to ship the data you have some more energy cost, but overall the gains would be more because the computation is really intensive.
So if this is an important point, your application has to be at least structured in a way that the computational intensive portions are not mixed with instructions that read the sensors. So you have a method that reads the sensors, and then another that is process data. Then the profiler will get information about how much information you are sending about this data, how complex this computation is, and how much output you will get. If sending this input and getting the output is actually cheaper than process this sensor data in the mobile itself, then yeah, you will offload it. So, let me go about the first actor in this plane, the MAUI proxy. The proxy will be responsible from intercepting application calls. Then with the help from the solver, it will ship the flow to the smartphone or to the mobile server, to the remote server. If it ships the state of the remote server, then it will synchronize the state. And if there is any problem, if your server disconnects, well, the proxy is responsible for handling errors. And handling these errors is very simple because, well, you have the state synchronized already just before the execution of this method. So if you fail here, what you do is you just do the same thing locally. Once your method finishes, the proxy will provide runtime information to the profiler in order to give information, in order to feed the solver with information about the runtime of your application. But how does this profiler look like? Well, the profiler, as I mentioned before, will take information from the network, the application, and the device. From the network, in blue, we will take information about latency and bandwidth. From the device, we are going to make a per device profile that will help us map all this information into an energy estimate. From the application, we're going to take this runtime information and a call graph that I will show in the next slide. The profiler will then tell us what's the estimation of the computational power cost and delay of running this in the model, or the estimate of the network power cost and delay plus the computational delay of running this in the server. This will come to us as an annotated call.
What is network power cost? Is that the cost of transmitting wirelessly?
Exactly. Okay. So this call graph looks like this, and I will show the call graph to actually make the point of why we care about this flow of the application, why we think that global analysis is required. Here is an example call graph from an application of a face recognizer. Here we have the user interface that is of course not remontable. Main method find match, an initialize face recognizer, and detect and extract faces that are helper functions. And here we have each node is a local invocation, and each edge is the cost of offload. So Let's take a look at different partitions and why this global analysis makes sense. We can, for example, just offload find match and do everything else in the phone. Well, for saving 900 millijoules, we will have to pay this and these ones to go back. To offload, it's better to look. So to offload just only face recognizers, we will pay 10,000 and we will be saving 5,000. So this is cheaper again to look. And the same will happen for detect and extract. However, if we do everything offloaded, we will only pay 1,000 millijoules and we will save almost 26,000. So it's, of course, it's cheaper to offload. Now, something that we wanted to show is that now we can adapt to changing conditions. And well, the mobile environment is very dynamic. You have connectivity changes, sometimes you're connected, sometimes you're not, sometimes you have high bandwidth, sometimes you don't. So, we have these changing requirements also in the way you use the application. So we took an experiment. We took like this very casual, simple, classic 1945 shooter game. And we modified it and added something very fancy, physics modeling. And well, for a phone like this in 2009, that was actually very hard to do. So we evaluated this under different latency settings. Here again we have a whole graph of these games. We have a main function do frame, a helper function do level, and 3 helper functions of that one that will handle the enemies, the bonuses, and the missiles. Each of these functions will usually take 11 kilobytes of space because that's the size of the level. But the missiles function will only take the missiles space. And when missiles take around 60 bytes each, so it's actually very simple. Oh, well, the state for this is small. The complexity of this one will increase exponentially with the number of missiles. And well, let's choose the first case. No missiles and very low latency. Well, in this case, actually, well, this is almost free. So most of the computation cost will be here. And we have very low latency, so it's cheaper to offload. Let's do everything of it. So that's what the format we will choose.
So are you showing the computational cost for the nodes in terms of energy secret?
No, but basically this one is very expensive as the number of missiles increase, and these are relatively cheap. They are cheaper at this latency than shipping this. Yeah, I don't have the unit with that. And in this second case, we have more missiles. We have 5. So if you were to do this in the phone, like it will crawl and it will be super slow. And we have some latency, 15 milliseconds. In this case, offloading the 11 kilobytes will actually be more expensive than doing these guys locally. But just sending 60 bytes, well, 60 times 5, 300 bytes is cheaper than doing this locally. So getting these two together, we only offload 100 missiles. Now, yes.
So how does the runtime know how many missiles? How does it monitor that?
Oh, well,
you
so
have to tell it exactly.
No, you don't tell how many. So it learns as you keep running the application. So every time you run a method, it will time it.
And it inspects the parameters?
No. So
it just takes longer each time.
Exactly. It doesn't read immediately. So you will have 3, 4, and then it was like, oh, this is too expensive. I guess the next time I should offload.
So
Yes.
you see that method is
Yeah. I mean, you could actually build profiles about applications so they start like to get warmer. But yeah, it learns as it goes. So, for testing this, we took like this one that I showed you and used the Monsoon that is a great tool. We tried 4 applications, a very simple chess game that has no AI. This is just to show that something as simple as checking the rules of chess can benefit from this offload benefit. And we have a face recognition application that is the one that I was talking about in the call graph. We have an arcade game that I showed both with and without physics. And to show that we can do very fancy applications that the phone cannot really do alone, we have a real-time English to Spanish, Spanish to English voice-based translator. So, when we evaluated Maui, we wanted to answer these 2 questions. Well, actually 3. Like the third one was whether we can run an intensive application like the voice translator. So how much energy and performance can we get from Maui? For energy, we have the face recognizer. This is a pretty nice graph showing a lot of savings. This one will be doing locally. These ones will be doing it over Wi-Fi, and this one over here is 3G, and this is increasing amounts of latency, 10, 25, 50, and 100 milliseconds. As you can see, we can save an order of magnitude of energy if we do this over Wi-Fi. And even if we do it on 3G, we can save quite a big deal of energy.
Another question. So
yes.
I kind of missed a little bit what the impact latency has. Do you have some threshold that says, well, it can't actually degrade performance too much?
Yeah, so it has a lot to do with the fact that all the time you're waiting for this input to come back from the network. Your device is in a high power state and your screen is on, and all these components are actually draining quite a big deal of energy. So the faster you can finish will have a pretty good impact on how much energy you're spending.
Okay, but you don't explicitly say, look, even if it saved energy, with 100 milliseconds latency, the application becomes unusable. I mean, there are some applications that would have that property, I imagine.
Where you cannot wait. What do you mean?
Where it would have been faster to just do it locally.
You burn more energy, but
you meet a deadline.
I see. Okay, so Maui puts energy at a higher priority. So you will rather save energy. Yeah.
You just try to save energy.
Yeah, okay. There's a threshold, like you will not slow down the application by more than a factor L. That we can
that's what I was asking. Was there some threshold?
Okay. Yeah. So first comes energy, and well, then as long as you don't like really. But in the examples that we tried, usually if you save energy, you save performance as well. But it may be the case that you some. And well, for performance, well, it was actually very similar. You save performance, you save time, then you save energy. And it was also the case for Wi-Fi, you save a lot more, and with 3G, you still save quite a big deal. But let's look at an example of a simpler application that doesn't save that huge amount of power. This is for that cake game without physics. In this case, we modified Maui so that it will actually always operate. In this case, when we do it over 3G, it actually wastes power in comparison to it locally. Normally, Maui will decide, well, just do this locally. But if we were to force offload, we will save more. What we can take from this is that if we have lower latency to our Maui nodes, we can actually offload more often and then save more energy.
It's hard to tell, though. The 3G is an outlier in the sense that you've only got one latency measurement.
Yeah, it's like an average. Yeah,
you meant. So when you say you could draw some conclusion about it doesn't matter what the latency is. The 3G is a special case. It's also a much more energy intensive communication.
So that part of the network profile also includes the radio consumption for Wi-Fi. So yeah, that will also be the case.
In your explanation to Bruce for why the latency matters, you said that you can turn the screen off faster. But for an arcade game, you wouldn't keep the screen on for a fixed amount of time, would you?
Well, okay, so if your game runs super slow, you will also take longer to finish a level, I guess. I guess that's like a different case.
It seems, I'm not sure I buy that. It seems like you're going to play the game for the 5 minutes of spare time you have.
Yeah, that's true. I feel that maybe, well, as I will show in the next half of the talk, probably mobile games are better handled by the other approach. And well, if you're playing games, the truth is that you're going to use a lot of energy.
So then how did you generate these numbers? What was the experiment? Did you sort of shut the screen off as soon as you got the results? Or?
No, so this is the energy consumed for running the game for a certain amount of frames. We will define a task as okay, let's play 500 frames of the game. And how much energy you take to actually run those 500 frames of the game. So yeah, if it's a finite task, you will save up. If you plan to play 10 minutes anyway, then you save that much power.
So most of the savings here is most of the savings the result of being able to turn the screen off faster?
It's a component. Yeah, it's a component.
Okay.
Is that you can reduce the power level of your CPU, so yeah, all that comes into play.
Right, so do you have a
So for these experiments, what was the screen brightness set to? Was it set to a high setting, set to a low setting?
It was set at the default setting, like medium.
Do you have a sense of the savings from letting the CPU go into a lower power state versus being able to turn the screen
So the main component of the energy consumption is actually the screen.
Right.
So the CPU is, depending on how, if you are like 100% CPU, like in the case of facial recognition, the CPU can be a large component. If the CPU is not that heavily used, it's not that a big component. So it depends on the usage. Like CPU can fluctuate a lot. I don't remember the exact numbers, but screen was the largest component, CPU at 100% was a close second.
But for the arcade game, 500 frames, does that take the same amount of time in either instance?
It will take much longer in the mobile alone because you are struggling to make it work.
But I mean, don't frames come at a fixed speed, like 30 frames per second or something?
And we render that, you will render all the frames. So if you were to do frame skipping, it will be different, but then your experience will be. So the game the game was able to do like 4 frames per second, so like it was not even playable. What games do actually, like they will do a certain amount of frame skipping, but if after it reaches some threshold, instead of skipping frames, it will slow down. So you will still render most of the frames.
Yeah, so in that case, the game just wasn't playable, feasible without
Yeah,
offload.
yeah.
So you didn't have a choice.
Yeah.
So the benefit there is mostly a performance benefit.
Yeah, yeah, and the performance benefit was, well, actually the performance benefit was pretty large. Like what I don't.
Can you tune the Maui solver to optimize for performance instead of energy?
Yes, you will need to change the linear program that you need to solve. So yeah.
Is it hard to do that, or is it sort of a straightforward change to the solver?
Well, you will need to. It's a simple change. You just need to change the objective variable, like for the LP solve one you have.
Different kind of question. I'm still stuck with the latency point.
Yes.
So suppose you actually offload some of the code, right? The order in which the events happen, could it be different than if you did not offload the code, if when you run the whole thing locally?
So they have to behave in the same way. We are going to preserve the application semantics.
But suppose it's a multiplayer game or there are multiple threads running, right? I shoot you, and if the bullet takes longer, or it takes longer time for that to get processed, someone else can move and I may not be able to shoot you, versus if I did it locally.
That's why you want Maui. So you
don't get shot
dead before you get shots.
So this has to do with some of the restrictions we place in Maui. So doing a multiplayer game will involve side effects. So that's something we don't allow. And well, having multiple threads will also be something we don't allow. So yeah, that doesn't work with Maui.
Does that restrict the scopes significantly, or so now you're saying single-threaded models?
So you can have one thread of computational intensive work, but you can have many UI threads that have no dependencies with these threads. Yeah, this is.
But then who figures out the dependencies? Who figures out the dependencies?
So you can only offload a thread, and if you have code that generates threads, the Maui compiler will not flag it as remotable, will issue a warning. So yeah, if you flag them as remotable, the compiler will tell you no, this is not remotable.
Okay.
Yeah, yeah. So like we pre-process the code and we generate this. So the Maui proxy, there is a Maui proxy per class, and each source class you pass them through a code generator and you get like the final source that will have these interceptions. And when you transform it is when you can find these glitches.
So I'm confused. Earlier you said that the programmer specifies what's remotable and what isn't, and I thought I heard you just say that the runtime is now telling you.
Yeah, I mean, so there are like some, you're expecting the programmer to find this out, but the compiler can find a little bit of these issues.
So the programmer specifies and the compiler says, oh, that is wrong, that is wrong, that is wrong.
So it doesn't catch them
The
all.
rest is fine.
Yeah, that's the thing. So you can have a single offloaded thread, and it will be legit. But if you have some threads that you claim that is like client only, but have some dependency with the offloaded thread, the MAUI compiler will not detect that, and yeah, you will be in trouble. So yeah, I mean, this is.
So can you characterize for me what class of problems where the compiler can detect that the programmer has made a mistake in specifying what's remotable and what isn't?
So in the current state, is like looking for the thread class. It's actually very simplistic, but with enough work, you can find more cases.
So you're saying that if you mark a thread as remotable, it better not inside that thread, inside the function, it shouldn't create threads itself.
Yeah, exactly. Yeah, exactly. So like if you have a remotable thread and it's reading state from another thread, or it's trying to pick a lock or something like that, that will fail.
So basically, you look for synchronization errors.
So I'm not looking for that, but I can look for that. Yes. I mean, in reality, it's probably better to trust the developer to find it because it's a hard game to detect. Right?
So your original stance is that it's up to the developer.
Yes.
And that's still your stance.
I mean, I am trying to help with the compiler, but it's like, we are not held responsible if you shoot yourself in the foot. It's more simple.
So maybe you could just clarify this point then. Can you explain clearly what the semantics of adding the remotable tag is to a method? What does that mean to the programmer and to the MAUI runtime?
The developer is saying, I here certify that this method is safe to offload because it doesn't have any side effects, is not accessing any other thread state, and is not using the sensors or the input or output.
But it doesn't have any side effects. It's kind of a difficult.
By external side effects, I mean it's not accessing anyone else that is not the mobile or the MAUI remote server. That's what I mean by external side effects. So if you don't have any sockets to someone else or Bluetooth communication.
So you're not talking about thread dependencies in that statement?
No.
Side effects.
I'm talking about external side dependencies. I mean effects to like an Amazon server, another game player, stuff like that.
But it can have side effects within the address file. It can modify object state.
That's fine. We can handle everything that your method that you uploaded can reach. We are synchronizing it.
Right.
So you can change anything of that.
Just can't write to the file system or talk to the network or have side effects.
Exactly. Yes. Yeah. That's exactly the thing. Okay. So let me go quickly about this because I'm taking note in this section. Okay. So MAUI will, in summary, MAUI enables developers to get a lot of benefits from power and energy and power and performance from an application with a very low barrier entry, and it adapts to the mobile changes in application requirements and network conditions. So now let's get into the next half of the talk that will be about Kavai, that is a system for offloading GPU applications. And well, this is important because mobile games usage has increased dramatically. So it turns out that 45-66% of mobile users use games. 49% of the time. Right? That means if you're using your phone 10 seconds, 5 of them are playing games. Let's see. Anyway, so mobile is lagging behind the desktop. And this is just by design. These phones are designed to be, some phones are smaller than a GPU. The heat they produce is much lower. Like if you, a GPU can get like 200 Celsius if it's super hot. They need like liquid cooling, for example. The price, a GPU can cost as much as a phone. And power, well, a GPU can consume probably 100 times more power than a phone. So yeah, it's completely different ballparks. And well, these kind of applications weren't really previously offloadable because they are continuous and they provide very large output. So what we have instead? We have this thin client approach. And there are actually many companies doing what is called cloud gaming. Companies like Gaikai, OnLive, and Ubitus, they do this thin client where you have a very big server that is going to do the graphics rendering for you and just sending the result of this GPU rendering as video. It makes sense to send it as video because this output is, well, one full bitmap 30 times per second or 60 times per second, so it just makes sense to send it as video. And this works because, well, depending on the game, most gamers can tolerate delays between 100 and 200 milliseconds. So that's still good enough to actually, if you have servers in enough places to have this delay and provide an enjoyable gaming experience. The problem is that with high quality comes high cost in terms of bandwidth. On live usually requires you to have, well, recommends you to have 5 or more megabits per second of network access. This is something you can get only when you are in your house and when nobody else is using Netflix or downloading whatever. And furthermore, this is restricting the environments where you can play these kind of games. So no cafes, no bookstores, no airports. You cannot play these kind of games when you're waiting in line. And well, if you're going to play games 49% of the time, well, this is important, right? But there is an opportunity here. We can use the mobile GPU to reduce this bandwidth requirement. And the proposition here is to use collaborative, what I define as collaborative rendering. Through collaborative rendering, the mobile device will render a low fidelity output, and it will combine it with the high fidelity information from the server to provide a high fidelity output. Now we're taking advantage of two different properties. First is detail fidelity and temporal fidelity. I will explain those in more detail in the next slides. And well, this work is characterizing these properties that are exploitable by Offload. So for the talk, for this half of the talk, I will go in detail about collaborative rendering and the two approaches I want to describe, delta encoding, with a short primer about video encoding, and then client iframe rendering. The first one will be about detail fidelity, and the second one will be about temporal fidelity. So the first question will be, cannot we just use MAUI for this? Well, we can think of it from two levels. If we want to think from using MAUI at a high level game method calls, well, we have a large output. The whole frame buffer, 60 frames per second, in a continuous way. This is, according to what MAUI gives priority, like this will use so much power that MAUI will decide never to offload just because of the expense. And it will be, well, pretty slow to just keep sending one bitmap at a time. And with low-level graphics code, well, if you were to take a look at how the the GPU works inside, it's a complex structure, and the way it works, it generates state along the way that is actually much bigger than the frame buffer itself, so that's not a good idea. And even if we could, the implementation of this graphics state is very manufacturer specific. So it's not like we can just reconcile the state from an NVIDIA GPU with an ATI GPU and just let it work. Doesn't happen. So instead, we're going to treat the GPU as a black box, and we are going to work with the output instead, and we are going to observe properties and take advantage of them. A very important point is that if we take advantage of the output, we really don't need to synchronize the state because the GPU is a black box. We need the output of this graphics application to be deterministic. That is, for the same user input, you will get the same output. And I will mention how we are achieving this in details. The mobile GPU can do part of the rendering, but how is this going to work? Well, through the technique I mentioned, collaborative rendering. But, so you can believe me about this. Let's take a look at how games work. Here we have a setting screen that is very common in many games. In this kind of screen, you can set many different effects, the resolution, the texture quality, model quality, etc. And you can just change it here. These screens are provided so that if you have a slower computer, you can still play the game, maybe with a lower detail fidelity, at a lower level of detail. So, let's take a look at some games. This is Ryu from Street Fighter 4, a very popular fighting game. This is a screenshot from a low detail version. And if we tweak the settings to the max, well, now this is Doom 3. Like, you cannot even see this guy's face, or you just see some kind of humanoid. The door has no detail at all. And in here, well, it changes quite a bit. It's the same game, you do the same things, but the experience is much better in this level of detail. So, after looking at this, we found the following properties. We have video settings that allow us to change the detail fidelity very easily. We don't even need access to the code to do this. And we saw that the low detail version captures most of the structure, as well as long as some properties that we will mention here are present. First, we need deterministic graphics output. That means we are going to do two executions, one in low fidelity and in high fidelity. The same thing has to happen. We need to have a consistent scene composition, and we need to have an overall simpler low detail scenes. So let's go over 2-3. Oh, yes.
So you said that you don't need access to the code in order to change the fidelity?
The detail fidelity, no. You just need to change the settings screen.
But isn't the settings screen part of the game?
You need to access the source code.
Excuse me?
You don't need access to the source code.
I see.
So
So
you
basically
just
what you're
buy a
saying is
game.
that the game exposes a UI that allows this.
Hey, Eduardo, can
Yes.
your gaming operations change based on what is visible? I didn't see the door, therefore I didn't escape.
So when you take a look at how the graphics work, they have it was kind of like a pipeline. And at some portion in this pipeline, the GPU will say, okay, I don't see this because it's very far, or because it's being hidden by something else that is in front of it. So like these portions of the objects that have to be rendered are discarded at some portion in the GPU process, yes. But that's at the level of the GPU, it's like very low level. And well, the GPU actually keeps a representation of the whole world. Well, not the whole world, but like a huge chunk of the world in memory all the time. That includes the stuff you cannot see, the stuff that is too far. Because, well, if you move, you need to have it ready so it's rendering the next step. So the state of the GPU is actually very big. Even if you are actually rendering and shading at each step is small, you keep all this in memory. But yeah, all this is filtered every time you render.
I think he was asking, does gameplay change in lower fidelity? And
Oh no, the gameplay is the same.
But that's a human experience thing, right? I may not see something. I mean, you showed a door that was not visible in low fidelity.
Oh, so the door is visible in both. It's just that it looks ugly in one. But yeah, I mean, you will see like a kind of like a solid slab in one, and in the other one you will see something that you can actually tell is a door. But
Exactly.
but
it's a solid slab, and I'm trying to escape. I may not just think that it's a door.
Well, if the quality is very low that you cannot even recognize, yeah, it changes. Usually they don't let you tweak the settings so low as that you won't recognize what's going on. But yeah, I guess technically if you have super low fidelity, yeah, it could change the experience. There are some other settings that can change
And
the
now I'm
experience.
thinking if it's a multiplayer game and someone's playing at a high resolution and I'm playing at a low resolution, that guy has an advantage.
There are actually no cheats for like multiplayer games. For example, some games allow you to have certain amounts of fog. If you disable the fog, like you can have some advantage in multiplayer games. So yeah, there are like some tricks about that. But usually the developers realize this, and in multiplayer they disallow you to change certain settings. Or they.
I'm surprised at you. I would have thought you'd be the kind of gamer to just blow a hole in the wall anyway.
Okay, so let me go about these properties first. So for deterministic graphics output, it's a relaxed form of deterministic reading. It's not in the sense that we have like the exact memory contents and the exact same execution, but for what we care, everything happens the same. What I mean here is that if you choose to, if you shoot a zombie in the mobile, you have to shoot and kill the zombie in the server. And if you shoot and miss and then you get killed, you should get killed in both sides. So the logical effect of the gameplay should be the same in both sides. And for the consistent scene composition, first let me define what I mean about scene composition. It's the set of logical entities on the scene. And well, they are the characters, the walls, the trees, the lamps, the bad guys, the weapons, bonuses, everything that is well logically visible and important in the game. And the light sources, the cameras, all of this is like the scene composition. And a consistent scene composition will have all the basic attributes of these elements having the same basic values. That is, the same position, the same rotation, in average the same color, and more or less the same shape. We are also asking the low detail scene to be lower entropy. That means lower high frequency pixels, like the amount of change in the information. Like it's less noise. And this is usually natural in most games because they use smaller, simpler textures. They use simpler lighting models. They use models with lower polygon counts. But it's not always the case, and I will show you soon why is that. Sometimes the low detail versions will decide to remove these very expensive effects and remove them for some like super cheap, low quality, but higher frequency one. Let's take a look again at the games. We have the same basic structure, the same guy, the same pose, the same facial expression, everything is the same. You can see that there is a guy that is about to fight involved. And here again you have the same scene composition, the same kind of floor, the same number of structures, the same number of guys in here, your viewfinders are the same. Here you have an overall humanoid shape that is mostly kind of gray, and you have a light here that is well bright, and you have a handheld that is brown and kind of black, and here well, all of this is consistent. Now here is a counter example on when this doesn't happen. This is from Lost Planet 2. This is low definition, and I guess for these guys going high definition means going green, because they had just much more vegetation here. This is a different scene composition. Like this is not the same. Now this is an example of a low detail scene that has much more detail. Here is low detail scene for Lost Planet and high detail. It turns out that the water here actually moves in a wave pattern, and here is just static there. So to make up for the movement in this side, they just use this fancier texture. It almost feels that this game was built to be an enemy of our technique. Because it was very easy to find those two in just one demo scene. Anyway, let me go about delta encoding. That is what we are going to use for games that expose these properties. And well, the solution for taking advantage of these properties is what we call delta encoding. In here we will have the mobile do what it can do well, just do load it. And the server will do what the mobile does and also a highest detail set. We are going to take the difference between those two and it will be a delta. Since those two scenes share most of the structure and most of the pixels are kind of similar, this delta will have less information than what this one alone will have. So we will send it to the client, and we were thinking, oh yeah, we're going to do great, we're going to beat video with this. It turns we don't, because we're missing something important that video has, and that's called temporal locality. To explain this, let me give you a quick review of what video compression works. We have two different types of frames here. We have iframes and p-frames in video. Iframes are pretty much JPEGs, and p-frames are predicted frames. They are frames that take an iframe as reference. Instead of encoding all the bitmap themselves, they just say what changed from the previous frame to now. These predicted frames take advantage of spatial locality, that's kind of like what JPEG does, and they take advantage of temporal locality, that I will show you just now. And temporal prediction works in the following way. Let's say that you have two frames. You have this frame that you already encoded, and you have this frame that you want to encode. So if you want to go from this to this, video compression will tell you, okay, we have these divisions here called macro blocks. What will happen if we move these 4 blocks to the right and these 4 blocks to the left? We will get this. That is, well, actually, I meant like, from this we are going to move the blocks this way. So from this we get this, just by moving the blocks, not doing nothing else. And this one is much closer to this one. From this one to get to this one, we just do a subtraction. And this plus the vectors is what we encode. And that's what makes video be so small, because you are just making a small difference and taking advantage of the fact that stuff moves gradually and slowly in video. So if we apply this to deltas, we just add the encoder, and we take advantage of temporal locality, because it turns out that these deltas do have the same temporal locality that the source has. Now, as I was saying, there are some cases when T doesn't work, like in Lost Planet. When you do this, you
You're
get
just
some
encoding the deltas.
exactly means sending a video of deltas.
Can you go back one slide?
Yes. Sure.
Yeah.
Oh, the
When
preview.
you, the one that you no, go forward there. So when you say the deltas, you're talking about what is the delta in this picture that's going to be?
This is just like for average video.
It's a residual end.
So pretty much we will make a residual of the residual in this case.
Okay.
Because the residual also changes gradually.
Yeah.
So it will be a residual of residuals. Yes.
So you're going to send the second derivative.
Exactly, it's the second derivative. And well, since actually, so this is compressed as JPEG, so this is lossy. We will have some amount of loss in here. So when we get this, we are not going to get the exact same version, but we get something very similar that is like competitive with video. And so when this is well, in this case, this doesn't work. So like it will look like this, because well, it turns out that to go like the subtraction of this to this actually has more bits, more information than just this alone. So this will get bigger and will get more compressed and will look worse. So what do we do about these cases? Well, we have something that is called like I-frame rendering. That is, well, it takes advantage of low temporal fidelity. That means the client, the mobile GPU can do high-detail graphics, but at a much lower rate. Instead of like doing 60 frames per second, you can do maybe 6. So it will look super choppy and bad if you look at it alone. But what if we let the phone do this 6 frames per second and we just supply all the frames in between from the server? You would expect that, well, if we are doing 20% of the frames in the client, we will save 20% of the bandwidth. It turns out we can save much more than this. And I'll tell you why. If you remember, when we are doing temporal prediction, we are using a reference frame. This reference frame is actually compressed as well. And if you compress your source frame, the errors from loss propagate to the predicted frames. And this error keeps accumulating until you get another full intro frame. So what's the solution? Well, if you put more bits into encoding the P frames, you can fix the noise, because it's the information you take to do the residual plus the information you take to undo the noise. But we don't want to add more bits.
So why does the error accumulate as opposed to, I mean, if you're just referring back to the same iframe, then why would the error get worse?
Because, well, we're assuming that you have a fixed budget to encode each frame. So you take a certain amount of bits just to encode the difference, and you will need another extra amount of bits to fix the errors.
But I think the P and B frames don't refer back to the original iframe. They refer each time you.
They refer to a previous frame.
They refer to the previously rendered or the next rendered frame, so that they're farther and farther away from the original iframe.
We are not using B frames in here because they refer to frames that cannot be rendered yet. So we are only looking at P frames. But yeah, so they keep referring. So like the P frame would refer to the previous P frame and so on. So yeah, that's why it propagates. Because well, the temporal difference between the iframe and just the previous frame will be larger. So you have like IPPP. If you refer from P3 to P2, the temporal difference will be smaller than if you go all the way to up. That's why we do that. So yeah, that's why this propagates. And well, the other thing you can do is you can insert more iframes, but these are big. They appear only like every 100 to 50 frames. But there is something we can actually do to get the best of these without using any more bandwidth. What if we use the mobile frames as iframes, as completely lossless iframes? We will encode all the frames in the server, and the frames that the mobile can do, we will encode them as iframes, so the streams match. We're going to send the missing frames from the server as P frames, and now these P frames will be either smaller or higher quality because there is no error propagation. And we will just reconstruct the stream at the client. That way we are saving the amount of information from the iframes, and we are getting a smaller P frames. It works kind of like this. We have a server game, the encoder, this guy will remove the iframes, and then we get this in the model. So we have the iframes that are going to be sent to the encoder. We are going to transfer these full frames into IFP frames. We are going to remove the iframes and send them to the mobile. In the meantime, the mobile will be rendering just those two iframes, and then we'll put them together, send them to the decoder. That most mobile phones now have this done in hardware, so this is super cheap, and we just display them. And that way we can get significant savings. Now, to evaluate this, let me just introduce you to what a game engine is. A game engine is the basic unit of game development reuse. Many of the games that actually are very popular are being done using game engines. They provide most of the basic functionality of a game, like collision detection, building a level from a script, enemy behavior, etc. So developers only have to worry about the content of their specific game. So this is actually very nice. And the good thing about this is that if we want to modify one engine for our system to work, we are going to benefit many games. So the end game developer doesn't have to worry about this. And well, we have to modify this engine to support deterministic replay and low temporal fidelity. That is, to skip rendering what the p-frames would do in the mobile GPU. And well, to support deterministic replay, we are going to intercept, for example, sources of non-determinism, like reading the system time. And well, so what we use? We use the ID Tech4 engine. This is known as the Doom 3 engine, from one of the games I showed, the one with like the guy standing in front of you. And we use three scenes. One that is a built-in benchmark demo. A friend was kind enough to play the whole game for me last week and get to the final boss and record a script for that. That was another game. Yeah, that's a friend, the one that will fight a cyber demo for you. And I have a very light scene in a right room. I did like 600 frames. That would be a 10-second rip. We encoded this using the out-of-the-shelf X encoder. This is the most popular encoder. This is the most popular decoder for H.264. That is like the state-of-the-art video compression encoder. And we play through SDL. This is not a hardware accelerated library. So for now we are doing only 48 frames per second. And I believe that once I apply hardware decoding to the prototype, I should be able to get the full 60 frames per second. And so for the hardware, if you want to take a look at my office, you will see a very beefy server with 6 cores and 3.2 gigahertz, and yeah, 2 NVIDIA GPUs.
Can I have that when you graduate?
That's London. Yeah, I guess this would be like a... People are fighting for it already. Yeah, it's nice. It's very nice. It's a pleasure to play with it. And for the client, we took like this 5-year-old netbook, laptop, that more or less resembles the computational and graphics power that a phone will have by the end of this year. So it has a Core 2 at 2 gigahertz, an NVIDIA 8400. That is the first NVIDIA to actually support hardware video decoding. So the question we wanted to answer with this evaluation is, whether can we provide high quality? So here we have a graph from the first demo, the built-in demo, that shows the perceived quality. This SSIMDB is SSIM is an objective measure of quality that will give you an idea of how good an image looks like. I adjusted the scale to be using the modified SSIMDB that is using a logarithm scale. It basically 10 times times the log 10 of 1 minus SSIM. So what it basically means is that 10 to 20 is great, below 10 it's terrible. For those familiar with SSIM, 10 is equivalent to 0.9 SSIM, 20 is equivalent to 0.99. So this is the range of values that matter. Everything below here is actually really bad. So a lot of people have used this modification when they want actually to show graphs of SSIM. And so, well, in here we can see that we are doing pretty well. This is the thin client. This is the amount of bitrate we need. And when this kind of matches the numbers we have, like it will be like 6 megabits per second to do like a good level of detail. But if we use deltas, we do pretty good. But even better if we do iframe, client-side iframe rendering. This is having the client do 1 iframe every 5. That will be 12 iframes per second. So it's more than just like the 20% benefit we will get. It's actually much more than that. For example, here we can see that while with just a little bit more than 1 megabit, we can get more or less the same level of detail that a thin client would get by using 6. Another thing, where we get again large benefits, even in very low bit rates, we get about 10, so that's good quality, and we are using less than 1 megabit. And we'll look at this. In this case, we're using 4 times less bandwidth than what a thin client is doing. And this is a particularly good case. This is a light room. I can show you actually like this here. And in this case, we have a room that is very well lit, and it's also a room in which I did this demo myself. I'm just walking slowly, like kind of like touring around the computer lab in the game. So it's slow, has a very good temporal locality. That means that iframe, pframe will do pretty good, and it does pretty good. Like we are saving like 8 times the bandwidth here. In this case, delta is not doing that good, but we still have some good amount of savings. And well, for the second question is, how much does the client helping the server affect this bandwidth reduction? Here we have iframe doing iframes 6 times per second and doing iframes 12 times per second. As you can tell, if we do more iframes, well, we can get better quality using the same bitrate. The same thing happens with deltas. Actually, it's much more noticeable in this case in deltas. Here for deltas, I define low quality as the built-in low quality. And that's what we get, and that's what I showed in the graphs. But what if we instead take low to be actually medium? Well, the detail fidelity will be much higher, so the quality that you can get for the same bit rate is, again, much higher. So, faster mobile GPUs will require less bandwidth to run the same game. And so, in summary about Kawai, so I showed that Kawai through collaborative rendering can take advantage of mobile resources and reduces bandwidth requirements through 2 approaches: delta encoding that saves through detail fidelity, and client-side iframe rendering that saves through exploiting temporal fidelity. And I also showed that saves of bandwidth are proportional to the mobile resources. And well, now for like the overall conclusion and related work, it turns out that there is like just plenty of work related to both of these projects. There are like 20 years in systems and 20 years in graphics. So we have work, for example, like Jules and David that worked in fine-grained offload like 20 years ago in the Emerald system, and Rajesh Balan that worked in Chroma, Spectra, code offload, very similar to this with a solver, etc. We have Clone Cloud by Chun that came.
Not to mention the Amber system. Not to mention the Amber system.
Yes, of course. yes. Sorry, yes. Well, we have Clown Cloud that uses threads as a level of fine-grained offload. We have application-specific code offload. This is like from RAD that takes advantage of stream applications for, like, for example, in machine learning. So this is like kind of like what I'm showing, that properties of application to do some specific offload. And the Lara used application aware offloading, where you, like similar to Rajesh, you change the application and you provide some expertise from the developer to do some smarter offload. In graphics, we have the work from Levoy, that is actually like the guy that proposed originally the equation I used for delta encoding. And what we, as different from him, we are actually using this for mobile devices, and we are taking advantage of temporal locality, that is, we are using video. Matt proposed having a set of frequent iframes, but instead of using pframes from a server to interpolate them. But there is a lot of video compression. There is what is called scalable video coding, and they are trying to take advantage of, well, many features in video about well, the fidelity in detail. So they want to have substreams with smaller content, and they let you switch on the fly. So that's kind of related to what I'm doing, but it's going to be the state of the art next iteration of H264, so it will be H265. There is work in deterministic replay. It's not for the purposes of doing games. There is work from Jason Flynn that is actually used in deterministic replay for offload, but it's done in a different way, where you have like two servers doing mobile and server, and they are doing the operation in parallel, and speculatively the server will try to finish first. And we have a lot of work on trying to take opportunistic advantage of resources. Well, there's a lot of work from Satya, a lot of work from Rajesh, work from Jason Flynn, and well, I could take tens of minutes talking just about how much related work there is in this area. And in conclusion, we have two classes of applications that are suitable for offload that will cover a large portion of the spectrum, graphics intensive and computation intensive. For computation intensive, we have Maui that takes advantage of unique properties of computation intensive applications, use profiling from the device graphical application, mixed with solver and high-level language features to provide savings in terms of power and performance with minimal effort. And we have Hawaii that takes advantage of the properties of graphics output and will use the mobile GPU in a collaborative way to get a reduction in the bandwidth requirements of the application. And that's it. So, the questions now. Thanks very much.
We'll do questions from the audience. How did you get the name Hawaii?
Oh, so Kawaii is Hawaiian for string.
Okay.
So it's very appropriate and matches Maui.
But I was just looking that up, and apparently
It's a salmon as well, it's a fish.
yeah, it's a New Zealand fish too.
Yeah, but it's a fish, and but I'm not talking about the fish, I'm talking about it's also a fish.
Other questions?
So from your graphs, it looked like the two approaches for graphics, that the iframe was always doing better than delta encoding. Is that true?
In this test, yes, it did better. But that's also because we used a pretty high temporal fidelity. If we include all the fidelities in here, if we have, like, for example, if we compare iframe against deltas with medium base fidelity, delta can do better in some cases. So you will choose the one that fits your device better. If your device can do better detail at 60 frames per second, then you will go for delta. If your device can get most of the features in a high-level setting, then you will use iframe. For example, if your game is using a lot of the features that the mobile device just cannot do, like anisotropic filtering, tessellation, stuff like that, and you want to have them, well, then you have to do delta. So that is like a compromise. Yes.
You're saying, are those things that a device might or might not have hardware support for?
So tessellation means that you are going to take a solid shape, and you can subdivide some of the polygons into smaller triangles. Yeah. And then these triangles you can just like pull them, so you can make, like in the case of the water, like in the game that doesn't work, you're using tessellation to make this solid water to be wavy dynamically. So that's a very sophisticated effect that comes with like the DirectX 11 cards, for example. That is very fancy, and well, mobile GPUs don't support it, for example.
Okay. So maybe we'll let Eduardo meet with the community then.